So in today's question, it's called contains duplicate 3. What do we have to do? So we are given an array of integers and we have to find out whether there are two distinct indices, so they have to be distinct, I and j, in the array such that the absolute difference between nums I and nums j is at most t, and the absolute difference between I and j is at most k. So if you look at an array and the indices, so basically the practical implication here is that if you have some series data and you want to find a near some element which is like near to the value which we are looking for, and also in the proximity of index, so that is what we have to find in a series of data. So it says that contains duplicate, but it's like a nearby value actually, right? So so the absolute difference has to be at most k. If this k was 0, then it would have been a duplicate. So let's look at some examples. So first one is 1 2 3 1, k is 3 and t is 0. So oh, I meant t. So the difference between nums I and nums j should be t. So if t is 0, that means we are actually looking at a duplicate, but we also have a range for indices. So here the index is 0 and here the index is actually 3. So the difference, absolute difference of index is 3 and the difference between value is 0. So yes, we have a value. Similarly, in this case t is 2, which means that difference can be at most 2, but the difference in indices can be at max 1. So yes, it is very easy. So like 1 and 1 is also there, 1 and 0 is also there because the difference is at most t, right? So we have it. So in this case, the k is 2, so the index difference should be k, and the difference in value should be 3. So we don't have any such value, so it is false. So if we look at 2, so if we start at 1, we can look at 1 5 9. If we start with 5, we have 5 9 1, but we don't have this 5. Otherwise we would have a difference of value 0, but we don't have it because the k is 2, so we can look only till 2 indices up or 2 indices down. Similarly for 9, 9 5 1 and 9 1 5, so nothing there. Similarly for 1, and similarly for this 5, and similarly for this 9. So we are not able to find any difference of value which is less than 3, and indices which are different by difference of at max 2, right? So so how to solve this, right? So one way is like we can just iterate over all the possibilities and see if that works, right? And actually that works. So I'll implement that solution for someone who might not know something advanced, but just want to solve this problem. So we will start with that and we will then look at some hints which they have given, and we will try to see if we can implement using those hints as well. So first let's try to implement the brute force kind of approach. So now what do we want to do is, so we are writing it in JavaScript. So now we have to iterate on every index and we will check for a window of length k that if we are able to find any element whose value differs by less than t. So that's what we will do. So and I, so this is what we want to do. And so the second variable will be j, which will actually iterate on the window. We will do I plus k, so this can go out of the range of array. So we will put a math.min, so when it is greater than the length of array, the maximum will be I plus, so maximum will only be till I think we should put it n minus 1, but that should not matter because, so it will anyway don't matter because we will be putting this, but we don't want to do this. So we want to start from up and we want to iterate till next element to I. So we are iterating from end of window to the front of window. For example, if we had, so if my I was, let's say, so the indices will actually be like this. So suppose I was 2 and let's say k was 3, then actually I will start from 5, then 4, and then 3. So basically I will check for all the elements in the on this side. I don't need to check on this side because so if we think about this, so for 2 I will only check the elements on the right side. Why do I not need to check the elements on the left side? That is because when I checked for 0 I actually checked 2. When I checked for 1 I actually checked 2. So that's why I don't need to look on the left side. So that's why I'll do it this way, that for every I will iterate from j, which is I plus k, and if it is more than n, for example if it was 4, then I will not have any index after 3 or after 3 difference. So I'll start with 5 only, which is this thing, math.min. So actually this should be n minus 1, and then j is greater than I because the indices have to be distinct, and then j minus. That's it. So that is what we need to do, and then it is very simple. We just need to check the absolute difference of the values of minus nums of j, that this absolute difference is less than or equal to t. So it is at most t, not equal to t, so that's why. Then we just return true. That means we have found something. So for every element, if we are not able to find anything in all the windows, then we return false. So that's it. So let's try it for the given cases. So we will take one true and one false. So the true one will already be there, I think. So we'll try for this false case. And the values are 2 and 3. So j has already been declared. That is because it should be a semicolon. So it is giving true false, which is what we expect. So we will try to submit it and we will see if it gives wrong answer, then we will correct it. So this is accepted. So this is a brute force solution. The complexity will be, we are iterating over all n, and we will be iterating over a window of k in worst case. So it will approximately be like, it will be bounded by so n into k, right? So that is the complexity for this. So this is, if you want to just solve that problem, so this is being accepted, so you can just submit it. So we will try to improve this. So I think you can also try to solve this in n log n by basically trying to sort some things, but we will actually look at the hint, so that we will so the hint is given for a solution which is n log k. So generally when you have a window of size k, so you can think about can you do something with that window. So that is exactly what can help us get a complexity of log k. So that is what. So they are saying that use already existing state to evaluate next state, like a set of k sorted numbers only needed to be tracked. Okay, when we are processing next number in array, then we can utilize the existing sorted state, and it is not necessary to sort next overlapping set of k numbers again. So let's think about what they are saying. So I will be implementing this solution in Java instead of JavaScript, because JavaScript I don't think has inbuilt data structure which can do what I require in log k. So let's go to Java. I think C++ also have some inbuilt data structures, but C. So we'll go to Java. So let me explain what they mean. So when you are having something like this, so suppose our k is 3. So now suppose so right now these are the values, but let's look at index only. So it should be like about idea. So suppose the window size is let's say it's 4. So firstly we will be looking at this window. So which is 1, 2, 3, 0, 1, 2, and 3. So suppose somehow I am maintaining that. These are the indices, and let the value be 1, then 5, then 4, and then let's say 19, then 2, then 1, then 3, then let's say 0. Right, so suppose the window was of length 4. So suppose now I have these numbers 2, 1, 5, 4, right? Suppose somehow I have these numbers in sorted order, or it does not matter if they are in sorted order, but suppose they are in any way from which I can extract this information, which is this. All right, so okay, so let's assume first that they are sorted somehow. So now if they are sorted, you can actually binary search over this window. So suppose we were at, so how we solved by brute force is, suppose you are looking at this value 1, and now the window will be this one. So when you're looking at 1, 2, 3, 4, so the window will be this one. So now you want to find a value which is closer to 1, but the difference should not be more than t. So maybe you can binary search it in this array somehow. I don't know, but let's say we can do. So if it is sorted, then we can binary search it in log k. So that way maybe we will be able to achieve this complexity of n log k. Right, so now what they are saying is, because we have already sorted these numbers and we are moving the window, when we move from 1 to 5, we are moving this window to next step. So actually we have 3 numbers which are overlapping. So somehow if we can maintain that order of these 3 numbers, then actually we can, so if we are not doing too much work while shifting the window, then we can just quickly shift the window and search it quickly in the sorted structure. Right, so you can think of how you can achieve this, but I will use a data structure which is called binary search tree, which is a balanced binary search tree. So what that does, it is that it will store these numbers, and it allows me these operations in log n time, worst case log n. So it allows me these operations. So add number, then remove number, then it allows me to find a number, then it allows me to find a number which is less or equal, find a number which is greater or equal. Right, so we need a data structure like this, and BBST can do this, which is balanced binary search tree. I think C also have some methods like upper bound, lower bound, but I'm not sure how they are used. But idea might be a little bit similar, but you have to maintain the order somehow. So when you're shifting from this window to this window, then that order has to be maintained. So because we can do add a number and remove a number in log n, so when we are shifting the window from this to this, right, I can just remove 5 and I can just add 1. What will that do is, it will take log n for removing, it will take log n for adding, and then I will do my find query using one of these 3. Let's see how, in log n. So whenever you are shifting a window, you will just do some like 3 or 4 operations which will all be log n, and the overall complexity will become n log n, because you will be shifting window only n times, n log k actually, because the window size will be stored in the data structure, because we will be removing the previous one when we move the window. So the complexity will become n for each element, and moving window and finding stuff in it will be n log k. So this is what we will try to do. Okay, so let's see how we can do it. I'll just comment this. So Java, I might make compilation errors, so let's see. So now if we want to, so I will tell you which data structure I will use. It's called tree map. So let's n be the length, and we will do tree map. So the utils package is already imported in Leetcode, so you can directly use it. I will tell you what I'm doing. Let's call it map or set or whatever. Tree map, and then long teacher. Right. So what we are doing here. So I said that we want to maintain a data structure. That data structure can just be a set, right? If there is so there is also one data structure for people who know Java. There is something called tree set. But the thing is, tree set can't store duplicate values, and it seems from the question that there can be duplicate values. So if we store the value in tree set, it will not know that there are multiple ones, and it might just remove when we have to remove this one. It will actually remove the presence of this one as well. So if you want to use something like multiset, you can use multiset, but I'll use a map in which I will store how many different so basically I'll store the value and the frequency. So if in a window it is duplicated, for example, I am in this window, and if I have to move this window, so in this window my value will be 1, but the frequency will be 2. So when I move to this window, I will just decrease the frequency, but then if I have to move from here to here, then the frequency of 5 will become 0, and when it becomes 0, I will remove it from the set itself. So that way we will be able to achieve that add and remove thing, and this tree map guarantees worst case login. So we will use this for size of n, but in this case our size will be k, so the complexity will be log k. So let's do it. So now what we are doing is now we can just iterate. Now actually one thing I will do is I will be storing the window which is behind me, and we will see how it goes, but just to mention that I will be storing window which is behind me. So now we take the current value, which is nums of I. So now what is the max upper value which we can match is current plus t, which is the lower value is current minus t. So okay. Cool. Right, so this is what we want. So basically this is our upper limit, this is our bottom limit. So if we are looking for a number, so suppose my current element was 5 and t was 2, then basically we want to see if so 5 and 2, so we want to see if the number is like 7 is the upper limit and 3 is the down lowermost limit. So we will do something with these numbers. So now, as I said, that we are able to find a number which is less than or equal to a particular value, right? So I will try to find a number which is less than. So we are looking at a particular window. You can just assume for now inside this loop, I will always maintain somehow that the size of this map is less than or equal to k. So when we are iterating over the array, I will keep adding, but whenever the size grow over k, then I will remove the last element. So the size of this data structure map will never be greater than k. So that means we are only looking at the indices which are closer to me than the difference k. So the data structure itself is maintaining this constraint for me, that absolute difference between I and j is at most k. So because we are looking in that range only, we just need to verify this constraint, that the difference in value is at most t. So my values will be key in this tree map, and integer will be the frequency. So for example, if this was the window, the frequency for 1 will be 2, and for all other numbers will be 1. So that is what we are doing. So now I will not add current number in the data set, but first I will check if I have a number which is less than up. So which is less than or equal to. So it will give me the greatest number actually. Not only a number, it find the greatest. So if the key which I am finding is present, it will return me that key. Otherwise, it will give me greatest number which is less than. And similarly, it can also give me find the lowest number which is greater than or equal to some number. All right. So that's what. So if I look at up, then what I want to do is so let's say my window looked like this: 2, 3, and 5, 2, 3, 4, to, let's say 0 1 1 0 and 0 and 1, 0 1 and 4. We are just assuming that it is sorted somehow. That data structure maintains it internally, but we don't need to worry. And let's say my current value is 5, right? So when I look at for this case, let's say this value is 6, and let's say we have 8. So suppose I'm looking at 5 and I look at up, right? So what will that give me is 7. So let's say t is 2. So now it will give me 7. So I need to find if there is any value which is closer to 5, like which is like in the range 5 to 7, like right. So closer to 5, like it should not be much further apart from 7. So the difference between them should not be more than 2. So because now I have value 7 in up in this data structure, I will find a number which is less than or equal to 7, like the greatest number. So which number is that? That is 6, right? So when I do this operation, which is okay, so I'll have to comment it. So if I do this thing, long up floor, I'm calling it up floor because it is the floor of up. We call it floor because it is the greatest value which is less than or equal to the given value. So up floor will be map dot floor key. So this is Java syntax. Then we just do up. So that's it. We found some value which is, I know, is the largest value which is less than up. So now what I can see is that value can be 6, right? So now I just need to find out first if up floor is not equal to null. So if there was no value, right? So if suppose the window was just like this, then there was no value which was less than or equal to 7 in this case, right? We are looking for 7. We are looking for 7. So in that case, actually this will give null. So we want to avoid that case so that we don't have null. So that's it. And the second thing is simple. So which is actually math dot absolute up floor minus up floor minus current. So we are taking absolute value. It should be less than equal to t. That's it. So if there is any value like this in the window, then we can just return true, right? So how can this fail? So suppose 6 was not there, then we are actually looking for 7 in this set, and what will be the value which will be given by this up floor? So it will actually be the largest value which is less than equal to 7. So 7 is not there, 6 is not there, nothing is there, only 1 is there. So when you check with 1, it is actually this difference, 5 minus 1 is not less than equal to 2. So that's that. In that case, this will not return true. So this will return true only when we have found our answer. So that's why. So and similarly we can do something like so suppose we had 4 here and we want to do similar thing with down. So down, now we are looking for 3. So now we want a number which is greater than, lowest number which is greater than or equal to, right? So now what we do is similar what we did for up, we do long down ceiling, right? So we do down ceil which will be equal to map dot, so it is not ceil but it is ceiling key, and we look for down. So now we are looking for 3 and we will be able to find something like 4, and we do exactly the same check. Down ceil is not equal to null, and the difference, the absolute value of difference between down ceil minus current should be less than equal to t. We return true. So let's just think about it, what we are doing. So if we are so what we did exactly in the upper value, we are doing that in lower value, that if you are able to find any value which is greater than my down value, like the lower limit, and the difference is less than t, then we return true. How can this fail? So if suppose 4 was not there, then we are looking for 3 and a value, lowest value which is greater than or equal to 3. So now we will only find 8. and 8 minus 5, or the absolute value of difference between 5 and 8, is actually 3, which is not less than or equal to 2, so it will not return true. So that's it. So in otherwise we can just return false. So I'll just check out where my loop is ending. So we can return false. Done. But we missed one important part, which is like we are not updating the window. So whenever I am looking at a number, now I need to add that number, right? So I will add that number. Okay, so this is the loop. So I will add it here. So so there might be a direct way to add that number, but I will put it something like this. So suppose that number was already there in my map, and I want to update its value, right? So I'm not sure if there is a quick way because Java, but I will do it this way. So I will do map. If map does not contains a key, it contains key current. So if it does not contains this key, then we will put something. We will put current and we will put 0. So why we are doing this? So that now we know that key exists and the second line will not fail. So map dot put, and we will just do current map dot get. We will get current value of the key and we will add 1 to it. Right, so what we did here was, so suppose the key was already there, then this line will not execute and it will just increase the frequency by 1. So that means in my window, so suppose the next number came as 1 and 1 was already there, then its frequency will increase. If it was not there, so suppose we were adding 3, then first we will add a value 0 and then we will, so we can actually put if else here as well, but I like to do this. So if you want to do if else, then you will do something like this. So if it was not there, you will actually just put 1, and else you will put this thing. So in this case you know it is there, right? So but that is how I do it, so I will just do it that way. But I think if else might be faster because only one of them will execute, but in this case both of them will execute. Cool. Yeah, okay. So and both are login actually, so this is actually very costly. We are just first getting which is login and then we are putting which is again login. So maybe if else will be better. So now we added that number, but now we have to take care of the case that when window size grows bigger than k, so suppose k was 3 and my window size grows greater than 3, then I have to remove a number. So how can I do it? So that is so we need to think about like when will it start growing. So it will start growing when I cross the integer index k. Right, for example, if the window size by 2, so if I am at index 0, then the data structure size is 1. When I'm here, the data structure size is 2, but as soon as I reach the value which is equal to k, then the data structure size will start growing and then we can start removing. So when will we start removing? If I minus k is greater than or equal to 0, right? So now we need to remove the value. Which value do we need to remove? So when we are reaching here and the window size was 2, we need to remove this. So we actually need to remove this 2. So which is like the index, current index minus k. So that's why we are also checking its validity here. So now we can just do key to remove. And what is that key? That is actually nums I minus k. And let's see if k is, what is the data type of k? So k is int. Okay, so where all I am using long, we have to just check that there can be any overflow. So current is long, so current plus t will be long, current minus t will be long. Everything should be long. These might fail, but let's see. Everything else looks okay. So I'll just put one L here just for safety, so that like if it is the max integer value and if we add 1 to it, then it should, oh, we are getting long only, then it does not need to be, but okay. So we need to take care of integer overflow if there are too many additions, like, but I think frequency will never get that big, but let's do it. So now we have a key which we need to remove, and how do we remove it? So now because this key we are sure that it will already be present in the array because we have already traversed it, so we will be putting it here. So we without checking we can just remove it. So how do we remove it? Actually, we will just decrease the frequency. How do we decrease the frequency? We just put it back. Key to remove map.get. So what we are doing here is we are decreasing its frequency, and now we just check map.get. So if it has become 0, so as I talked about earlier, if there are duplicates and if the frequency becomes 0, then and only then we will remove this key, and that's it. So what we did here was, like, we just in these lines we just maintained that the data structure contains at max k values. So we removed the previous one and we added the new one, and in this part we are just checking if there is a number which is close to us, like the absolute difference is less than t, using this floor and seal kind of functionality. So we will run it, and I'm totally expecting some compilation error because I'm typing everything without autocomplete or anything. So let's see, and hopefully we will not get null pointer, so it's okay. So long cannot be converted to integer. Okay, because the frequency isn't. So I'm getting integer here, so this should actually be int because the frequency here isn't. So the only place where I tried to prevent integer overflow was compilation error. So true false. I'll just for safety run the third case as well, so that so 1 and 2. So there can be, in Java it is very easy to get null pointer exception. So I will just run it in case. So true, true, false, so which is expected. So I'll just try to submit it if it gives any exception or wrong answer. So this is accepted. So I will just repeat once what we did. So what we are doing is so basically for any index, so right now, as I told, I am storing the elements which are behind me. So suppose I am at this index and I am storing values like let the window size be 3. So currently my data structure will have these 3 elements, and I will, in that data structure, using these functionalities, which is like the greatest number which is less than the lowest number which is greater than or equal, we will be able to find a number which is if there is any number which is close to me, like the absolute difference is less than t. So that we will try to do in this window. So now once we have, so basically thing to notice is when we are looking at this window, we don't include 5. After we are done looking, then we add 5. So when we add 5, now the window size increases to 4, but it has to be 3. So we have to remove this element, and how we are removing it is like we are decreasing its frequency, and if the frequency is 0, only then we will remove it. Why? Because suppose my window was this, and I moved one further, so I moved here. So now the 1 is out. If you just remove 1, then actually you will miss this 1 as well. So that's why we are decreasing frequency. But now the frequency is 1 because earlier it was 2. Now it will be 1. So that means that we don't have to remove that key right now. So that is what we are doing here. So hope that makes sense. And I did it in Java because I'll have to use some external implementation for this data structure, and Java already has it. So we are using that. So that's it for today. Thanks.